Hi there. Welcome to another problem session. So today we have another classic problem in application of Faraday's law. Um, the Let's describe the problem. So I've drawn a ring at two different times. So this is a time in which part of the ring is in a magnetic field region and part is not. It's moving through the magnetic field region. At this time, to maintain a constant velocity, you need a force, which I have not shown. So you actually need a force here in that direction, which I'm going to call external force. Okay. Then at another time, you have ring moving at constant v, but all of it is in entire region has magnetic field, and magnetic field is uniform. It's the same value everywhere. Okay. If it was not uniform, there will be a additional effect, but I'm talking about just uniform magnetic field. By uniform mean the magnitude of magnetic field is same, and by constant it mean the magnetic field is not changing with time. So uniform in space, and constant refers to in time. Okay. So a couple of things. So in this situation, that's the question part A. Part A of question says, when I'm in this situation, find current that will be induced in the in this ring, and find this. So there's some current going around, induced current, and we'll use Faraday's law to find that induced current. So if you can find EMF, then we can just do V equal IR, and because EMF will be steady, I will be able to use V equals to IR to just get the current. Okay. And the direction of the current is already included in the direction of the EMF, right? A direction of the electric field. So direction of the electric field that will be in the wire will be the direction of the current in the wire. So that's just we're gonna get it from the sign when I do this calculation. So that's and second thing is supposed to find the expressions, find the external field, external force that I'll need to maintain constant velocity. So that means there is a force that I need to balance, right? There's electromagnetic force, and I need to balance by applying external force. All right. There's actually a magnetic force. We'll find out while we do the problem. So you may have done this problem by another way, but we will just try to use Faraday's law directly, and then we'll see how it goes. All right. So if you know how to do this problem, maybe you want to do it and wait, then come back and check with my answer. You can just search for my answer of in here. Okay, let me pause the video, and I'm going to clean up something and then give you the answer, my answer based on Faraday law. Okay. Okay, so we are going to do apply this, right? Apply this law. And so this is some circuit in space. So this is some circuit in space, and you go around the loop in a oriented way, and that should equal to minus d dt of this integral that whose boundary is this C. So this is a surface, and you have a B. This is a surface integral. Okay, so I need to figure out how to implement this. So this is some boundary. So that's oriented C, and then we can say this is the area that's enclosed, and we're going to use the flat area. This can be this is the area surface A, or if you had the same boundary but some other surface. So this will be the S, but we don't need to be so complicated. Here we'll just have a surface area S. But the problem with this is our loop is actually moving, right? So this is a physical loop that's moving, and this is a mathematical or in space, and they can coincide, right? So to coincide, I'm going to say, imagine I have a coordinate system Y and X, and O is kind of fixed to this. So this is at time t, and then a little bit later time, I'm going to have this thing kind of move. So this loop will be over here at little bit later time. This loop, the wire as well as the loop in the space will have moved over here. So if I look at this loop, I want to have an orientation in the loop, the direction. So I will just pick a direction, and that direction, say this n hat, has to be used right hand rule on this loop, this direction of the loop. So if I pick a so this is going to be at t plus delta t, and this is the situation at t, and so this area is going to be at t plus delta t, and the other area, this thing will be for the area for the t, and this area for t plus delta t. And so right side I'm going to do is do the integral b dot n hat dA at t plus delta t, and then do the same integral b dot n hat dA at t, divide by delta t, and take a limit t goes to 0. So that's the way right hand side going to be, and then minus sign for that. So right hand side always going to be easier to do it this way. Okay, it's always easier in a problem situation. So let's do it like here. So I'm going to get the loop direction, I'm going to have this direction for the loop at t plus delta t is the same direction for the loop at t, so that which the right hand rule is coming out. So this will mean n hat is coming out, and which is the same direction as b. So if I do b dot n hat, that's just coming out, and dA is going to be the area of the loop. When I integrate, this is all constant, so this is going to be equals to minus limit delta t go to 0. So I have a delta t. If you look at if this is the this is a v times delta t, that area will be the additional b non-zero area, right? So you can say I have this area here, which is 0. Earlier used to be this whole area. This area used to be 0. Now you have just a little bit this 0. So this whole thing will become b dot v delta t times this width. That's the from this thing is, I'm calling it w. So that will be the change between these two, and so delta t will cancel out, and it's going to be minus b v w. So that's going to be equal to so we just found that E dot dl just be equal to minus BVW, and that's equal to minus EMF. Sometimes say minus induced. So EMF induced is equal to BVW, and this acts in a steady situation. See, this is constant, this is constant, this is constant. So this is some constant, right? And so that means like a steady EMF, and this steady EMF acts like a voltage in a DC circuit. So it acts like a voltage in a DC circuit. We don't have a DC circuit, we have a loop of wire. And so if you look at what this is EMF is coming from, it's as if there is an electric field non-zero, right? So if you look at this thing, then it says that this EMF is actually coming from the electric field. So the electric field is non-zero in the wire. That means there's a current in the direction of the electric field. And because E dot dl, this is E dot dl is less than 0 because of that negative sign, that means current, the electric field is in the opposite direction to dl, right? Opposite direction to dl because of this negative sign. And so dl was this way, the current will go, that means the current will flow this way, and amount of current will be amount of current I will be just E induced over the R. This is from applying Ohm's law to a steady circuit, and I have a BVW over R. So that's the current, and so that's we found part of the answer. Okay, so to summarize, so for the part A, we found that E dot dl equals to minus BVW, and we found current flowing in that direction, current flowing, this is clockwise, current flowing is equal to this divided by BVW divided by R. Okay, so if the current is flowing this way, let's call it I is flowing the same as the E field, current is flowing that way, and the magnetic field is out, then you can see that the magnetic this would mean the current is flowing this way over this part of the wire. So let's call it A, B, C, and D. I'm going to call it E here and F here, the parts that are, so this part is in the magnetic field. So just look at A and B part. In the A to B part, and magnetic field is up. This is the B field. That means using right hand rule tells me the magnetic force will be that way, and there is no external electric field to act on the charges. So this is all the force there is, this electromagnetic force in the wire, and I need an external force to balance it. So this will be the external force to balance it. So magnetic force will be this current times the length of the wire. So F magnetic force on A to B is going to be to the left, and it's going to be magnitude is equal to I L. L will be the A to B, L A to B, I L and the B, that's magnetic field, and that's equal to B V W over R, and LA to B is W, and then B. So there's a 2 factor V and 2 factor of W, so this is equal to B square V W square over R. How about A to F? A to F is current. A to F, the current is this way, magnetic field is that way. So if I do it, so this will be, the magnetic force will be that way, and if I look B to E, current is that way and magnetic force is that way, and they cancel. So this is the only magnetic field I need to balance. So this is the only I need to balance. So the F external that I need is equal to that direction, which external force is that direction, and has to be equal to this B square V W square over R in magnitude. So that's the answer for part A. Okay, let's try to do answer part B. Okay, for part B, you can see that when say time, this is time t, and then a little bit later on it's over here, and flux through this and flux through the original, no difference. So if I do limit delta t goes to 0, this right side integral b dot n hat dt at t plus delta t minus same thing dt at t divided by delta t, these two are exactly the same. There's no difference, so that's equal to 0. So that would just make the EMF, induced EMF, is equal to 0, and this is equal to minus E dot dl around any loop that we just want things. This will just this will cause the induced EMF 0. That just means that I induced is also 0. That means the F magnetic field, force of magnetic field, will be 0. Even it's moving, but because magnetic flux situation is not changing, magnetic flux through the area of the loop is not changing, you going to have no current, no induced EMF, and so no induced current. So no magnetic field means external field, external force required is 0. So it actually is going just by inertia, moving at constant V just by inertia. You don't need any other force to actually pull it. Now when it goes all the way to the end, now you're gonna need a force again to either pull it this way or pull it that way. So you will need force when this thing goes all the way to the end and it starts to exit. So suppose this was the end of the all magnetic field, and if it's now when you want to maintain a constant V, then you will need a force here also. Maybe you want to work that out. Work out I induced and F external for maintaining constant V. It's going to actually slow down when it comes out if there is no external force. The current will also be in a different direction when it's exiting than when it was entering. So you want to work this out. This is a good exercise for you. Okay. So these are the answers for part B. Okay. So we are done. If you like this kind of explanations, very straight, straightforward, and using fundamental laws, please hit a like button. That helps this video kind of get more traction and good distribution. Subscribe to this channel. Tell your friends to subscribe to this channel. I'm posting lots of good videos, and maybe check out also my website. This entire textbook that I wrote is on this website. That textbook is used in many universities right now. So hopefully you're learning something from it. Take care and bye.